This lecture is an overview of stream ciphers. We will also look at the inner workings of two popular stream ciphers, RC4, which was implemented in software, and A5/1, which was implemented in hardware. So a typical stream cipher is a symmetric cryptographic technique which encrypts plain text 1 byte at a time, although it can be designed to encrypt units larger than 1 byte at a time as well. Now this figure is a representative of stream cipher structure. In this structure, a key which acts as the seed is input into a pseudo-random byte generator that produces a stream of 8-bit numbers that are apparently random. So the pseudo-random byte stream is supposed to be unpredictable without the knowledge of the seed, which here is the symmetric key. Now the output of this pseudo-random byte stream generator is also known as a key stream, and it is combined 1 byte at a time with the plain text byte stream using an exclusive OR operation to produce our ciphertext byte stream. Similarly, at the receiver side for decryption, each byte of the ciphertext is then XORed with each byte of the key stream to generate the plain text. So the key stream for decryption is the same as the key stream for encryption because they're generated using a deterministic algorithm using the symmetric key as the seed. So we typically use stream ciphers where we need to encrypt or decrypt a stream of data, such as over a data communications channel or a browser web link. For applications that deal with blocks of data, such as file transfer, email, and database, block ciphers are more appropriate. However, either one can be used virtually in any application. There are some design considerations to keep in mind for stream ciphers. Number one is that the encryption sequence should have a very long period. Right, the pseudo-random number generator uses a function that produces deterministic stream of bytes that eventually repeats. Right, so the idea is that the longer this period before which it repeats, the more difficult it is to do cryptanalysis. Right, so the length of this key stream before it repeats itself should be long. Number two is that the key stream should approximate the properties of a true random number stream as much as possible. For example, there should be approximately equal number of 1 bits and equal number of 0 bits, right? And all the numbers appearing in the key stream should be equally likely. The more random appearing the key stream is, the more randomized the ciphertext is, making cryptanalysis more difficult. Number three is that since the output of the pseudo-random number generator is conditioned on the value of the input key, therefore to guard against brute force attacks, the key needs to be sufficiently long. So with the current technology, today a key length of at least 128 bits is considered secure. So all symmetric encryption techniques, be it a stream cipher, be it a block cipher, they need to have a minimum of 128-bit key size. One advantage of stream ciphers is that they are faster and use far less code than block ciphers. So we will look at the RC4 stream cipher shortly, which can be implemented in just a few lines of code. However, in recent years, this advantage has diminished with the introduction of the advanced encryption standard block cipher, which is quite efficient in software. Okay, so let's look at RC4, which stands for Rivest Cipher 4 and is the most widely used of all the stream ciphers, particularly in software. Why is it called RC4? Well, it was Ron Rivest's fourth out of his 6 algorithms. However, only this one was a stream cipher and it is widely used. The other ones were block ciphers, but not really used as much. Some of them were never actually implemented, and their code is also not published, for example, for RC1 and RC3. RC4 uses a variable key size as input, anywhere from a minimum of 40 bits, which is 5 bytes, to 2048 bits, which is 256 bytes. So this key is used to produce a key stream, which is then used to encrypt byte data. It has a very simple and efficient implementation, since encryption and decryption is just a simple XOR operation. Now, it was used for secure web browsing via the TLS protocol for quite a number of years, but now AES is recommended. RC4 was also used in the wired equivalent privacy protocol, or WEP, as well as for the Wi-Fi protected access protocol, which is also used in Wi-Fi security. However, now AES has replaced it, not because there were limitations in RC4, but due to the way in which keys were generated to be used as seed input to RC4 key stream generator. So let's look at the pseudo-random key stream generator for RC4 algorithm. Now, the first step is to initialize a 256 byte state vector S. And then we also have a 256 byte temporary vector denoted by T here, right? So we have 2 vectors, both of them have 256 bytes, numbered from 0 to 255. So we initialize S2 values from 0 to 255, as you can see here in this for loop, which runs from 0 to 255. We also initialize this T vector with repeating values of the key. So if, let's say, the key is A, B, C, D, E, F, G, H, where each character is 1 byte, then T will have values A, B, C, D, E, F, G, H, A, B, C, D, E, F, G, H. So we just keep repeating it until we have 256 bytes. And of course, in reality, we're actually using the decimal version of each of these characters, because we are dealing with numerical values here, as we will see in a while. The next step is to do an initial permutation or shuffling of values in the state vector S, because so far we have just numbers from 0 to 255 all in ascending order, right? So there is no shuffling. So what we do is we use the T vector to permute values in the S vector, as you can see here in this for loop from 0 to 255, right? So what we're doing is we are using this formula to choose some index j. This formula is using the current value of index j and adding to it the value of S vector at index I and the value of T vector at index I, and then we take a mod of this value with 256. And the reason for doing the mod operation is that if the value is greater than 255, we need to wrap it back to a value from 0 to 255, because we only have indexes from 0 to 255. And then we swap values in the S vector at index I and index j. This makes sure that all values in S are shuffled. So let's say we start with value I equal to 0, value j is equal to 0. So we try to calculate the j index using this equation right here. So we have j equal to 0 plus s of I, or s of 0, let's assume it's the value 0, as we saw in the previous slide, and then t of I, or t of 0, and let's assume the numerical value there is 4. This is whatever is the first byte of the key. Okay, so this gives us j is equal to 4 mod 256, which is equal to 4. Right, so what we're going to do is we're going to swap s at 0 with s at 4. So basically whatever we have here will come here, whatever we have here is going to come here. And then we keep doing it. Then finally we use this algorithm continuously, as shown here by the while loop, to pick a key byte from this S state vector. Now this key byte is what will be XORed with a plain text byte to generate the ciphertext. Now inside this while loop, we are picking two indexes I and j first, and then swapping values in the S vector at those two indexes. So you can say that, okay, we are doing shuffling once more. And then we choose another index t by adding the S vector values at this new I index and j index, and then taking mod 256. And then whatever we get is an index value, and then we take s at that index value as our key byte. Finally, encryption and decryption is simply XORing the current keystream byte with the current plain text byte to generate ciphertext, and then decryption is simply taking the current ciphertext byte and the current key byte and XORing these two together to get back the plain text. So let's look at the pseudorandom key stream generator of another popular and one of the oldest stream cipher, which is the A5 stream cipher. Now this was developed around the same time when RC4 was developed, and it was used to provide over-the-air communication privacy in GSM mobile phone systems. So this stream cipher uses shift registers, which means that they were meant to be built in hardware. And we use a 64-bit secret key as a seed in A5/1 stream cipher. And so the type of shift register we use here is a linear feedback shift register, or LFSR. And so shift registers technically are a type of logic circuits that can be used for storage and transfer of binary data. And they're commonly used in calculators or computers. When we say linear feedback shift register, it's basically a shift register whose input bit is a linear function of its previous value. Right, so I have an example here to demonstrate that. So let's assume this is a linear feedback shift register, which is storing 16 bits, sorry, and then we are going to have some kind of a feedback function, right? So this is actually the feedback function, which is technically just XORing certain bits. So we are XORing 11th bit, 13-bit, 14-bit, and 16 bits. This is representing XOR operation. And the result of that is what we are going to feed it back to this register, right? And before we actually feed it back, we just mean that we are going to right shift the current input by 1, which means that we're going to lose this last value. And then at the first location, we're going to put the output of the feedback function, right? And then we just keep repeating that in each cycle. So in A5/1, we actually have 3 linear feedback shift registers, okay? And the first one is 19 bits, labeled here from 0 to 18. The second one has 22 bits, and the last one has 23 bits. Right, so 19, 22, 23 gives us 64 bits, which is equal to the key size that this stream cipher uses. Notice here that each register has a set of bits that are XORed, and the result of that is placed in the leftmost bit of the register after, of course, right shifting the input by 1 bit. Right, so here we have certain bits in the first register that we're XORing. This is the feedback function, and then same thing for the second register. We have 2 bits that we're XORing, and then in the third register, again, we have 4 bits that we are XORing. Now, whether we actually perform this function, which means that whether we XOR these bits or not in a cycle, is decided based on what is known as a clocking bit, which you can see here in gray. Every register has one clocking bit. This is the 8-bit label here, the 10th bit labeled here, as well as the 10th bit labeled here. So we basically do what is known as a majority vote on these clocking bits in each cycle to decide which registers are going to be active, meaning that they will perform their XOR functions. So for example, if we have 0 as the clocking bit for the first register in the current cycle, and then 0 as well for the clocking bit for second register, and then we have, let's say, 1 as the clocking bit for the third register. Now, if we take the majority vote, we have 0, 0, and 1. Majority vote basically means which bit is in majority. This is basically 0. So, which means that in this current cycle, register 1 is active, register 2 is active, whereas register 3 is not active. So, it is not going to perform its function. It's not going to do the right shifting. It's not going to place the output of the function in this bit. Okay. Now again, if we have 1, 1, 1 currently as the clocking bits, this means the majority vote is 1, which means that all 3 are going to be active because all 3 clocking bits have the value equal to that of the majority vote. So here is the process of generating the key stream. So here we basically generate key bits instead of key bytes. So first step is to actually fill all these registers with the key bits, right? So we have 64-bit key, and what we're going to do is we are going to fill these 64 bits in the register with the key bits. And then what we do is we perform that majority vote function on the clocking bits of the 3 registers, and then the registers with the clocking bit value equal to that of the majority vote are going to be active, which means that they are going to perform their respective XOR functions. Then what we do is we right shift these active registers by 1 bit, and then the result of their XOR function operation is added to the leftmost bit of these registers. And the final step actually is that we take the rightmost bit of all 3 registers, whether it is active or not, and then we XOR them together to get our key bit for the current plain text bit or the current ciphertext bit. All right, so let's take a look at an example. So assume here we have filled up each of these registers with the key bits. So we have put the 64 bits of the symmetric key in these 3 registers. So first 19 here, next 22 here, and next 23 here. So first step now here is to find the majority vote of the clocking bits, which you can see here in red. Right, so we have 1, 0, and 1, and the majority vote of that is 1. So basically register 1 and register 3 are going to be active because their clocking bit value is equal to the majority vote value. Then the next step is to perform the XOR functions of these active registers, right? So what we're going to do is we're going to XOR these bits right here in each of these registers, and we're going to calculate their value. So for each of these registers, we get a value of 0 after performing these XOR functions. Now, we're not going to feed back the value of these XOR functions yet. We are going to first right shift each of these registers by 1 bit, which means that we're going to lose the last bits here, right? So basically, we end up with a 0 here for the first register because this value is going to move here. And same thing here, we're going to have a 0 at the last position because we're going to move this 0 to the last position. Then we're going to put these two values at the first bit location for each of the two registers, right? So we have a 0 at the first location for each of these two registers now. And finally, the last step is to XOR the very last bits of the 3 registers, whether they're active or not, right? So this will give us 1. We have a 0 XORed with 1 XORed with a 0. So this one gives 1, and you XOR this with 0. This gives you 1. All right, so pause here and complete this exercise. Assume that this is the current state of each of the 3 registers.